Let's talk about distributed generation. The first part of this has already been presented by Andres, but I believe that he stops. Let me start here because I don't know if what he said, but basically power electronics are used on motor drives, power supply, electric vehicles, aerospace and defense, power systems, and renewables. And there means, doesn't mean deer, right? I haven't forgotten, you know. You are in Arkansas, you never know, right, what they're thinking at this time of the year. So this means distributed energy resources, right? That's what there means. And so you have semiconductor devices. The next few years, you're going to see a push for silicon carbide devices. They are maturing those devices. And so you are going to see that they are going to be applicable, right? And they're going to displace silicon devices. So you are going to be using a MOSFET, but it's going to be a silicon carbide MOSFET. You are going to be using an IGBT, it's going to be a silicon carbide IGBT. These devices, they have lower switching losses. And so for those applications where switching frequencies need to be higher, you are going to see that these silicon carbide devices are going to be replacing. Already the Schottky diodes are replacing the normal diodes. So it's very common for motor drives to have a silicon IGBT working in parallel with a silicon carbide Schottky diode. The advantage of the Schottky diode is that it doesn't have a reverse recovery current. So it brings a lot of. And very soon you are going to start seeing a silicon carbide diode connected in parallel, in anti-parallel connection with a silicon MOSFET, 1200 volts or 1700 volt devices. As the modules become available, designers are going to start using it. And here is the Schottky diode, right? Thyristors will still have, right, that's the symbol for the thyristor, this is the symbol for the diode. And then you will have controllable switches, which are VJT. VJT are sort of falling off, right, for some of the applications that we are using. Why? What is important when you select a controllable switch, right? What is important? Sorry? Well, what is important? Right. Well, I think what you are saying is ease of control, right? Whether, you know, can you control it easily? Also the switching losses and conduction losses. Those are the things that you look at. How do you control a MOSFET? You apply a voltage, right? 15 volts to turn it on, and you apply 0 volt to turn it off. Very simple. The thyristors and VJT, they have a more cumbersome gate driver. So ideally, you would like to use the MOSFET. The MOSFETs are very good when you have to use 200 kilohertz, 500 kilohertz. The IGBT is a hybrid. It works It's a combination of a VJT and a MOSFET. But it can be also turned on by applying a voltage. It's called a voltage source control. Basically what you have here, and this is what you have. You know, this gives you an idea, right? The MOSFET can go up to 1 kilovolt, no more than 100 amps, right? But the switching frequency can be very high. Well, the IGBT, which is used in motor drives and some UPS and things like that, can go to a higher voltage level, can go to a higher current, but the switching frequency cannot be very high. The GTOs and the thyristors are the typical power devices or utility devices, right? You can see that they can go up to very high current voltages, but the switching frequency is very low. Well, this is applicable to silicon. This figure cannot be applicable to silicon carbide. For example, Cree is developing a 10 kilovolt MOSFET. The government is funding work at Cree to develop a 15 kV silicon carbide IGBT. Now, the IGBT will not, the first generation, I don't think that at 15 kV is going to switch at 100 kilohertz. So that, 20 kilohertz, 10 kilohertz, those might be the limits. But like I said, that figure will be, the devices will be the same. They are already silicon carbide thyristors. The only thing is that the IGBT will be able to give you 15 kV, which a better performance. So probably the thyristor may not have really an application. Now, so what I'm going to talk is about distributed energy resources, right? And what are those resources? Photovoltaic, wind, microturbines, fuel cell. Microsoft just announced that they're going to use in Wyoming, I think it's a server farm that they have there, they're going to use gases from a waste treatment plant to using a fuel cell to generate electricity to power the server farm. And so distributed generation, right, or distributed energy resources are going to change the landscape. Most of the relay systems that you have, they are all unidirectional. You have a substation, you have a feeder, like you have just model, and then you are going to basically power comes from the substation to the loads. When you have distributed generation, now in the middle on node 7, you are going to have power being injected, power going to flow. Well, whatever are the operating conditions at that time. And what does it happen when you have a fault? Well, your distributed generation is going to contribute to that fault current. So what about if you have a circuit breaker that has been designed for unidirectional power flow, and now you are having a distributed generation that is going to add to the fault current and is going to exceed the ratings of that? Well, there is something here. PCC stands for point of common coupling, right? Is that point where the distributed generation is connecting to the grid. The good thing is that here you have semiconductor devices. A semiconductor devices cannot provide fault for more than 10 microseconds. Uncontrolled, right? Uncontrolled current. If you short circuit the output of an inverter without any protection, after 10 microseconds, everything is gone. 10 microseconds is 10 divided by 1 million, right? So what do you do is you have very fast controllers that are going to shut down your inverter. Because if it conducts the fault current, how long was the recloser conducting the fault current? For the instantaneous curve was how? 2 cycles, right? What are 2 cycles? Right, 36 microseconds, milliseconds, right, milliseconds. 16.7, yeah, probably under 34, right? Milliseconds, not micro, milli. And then what was another thing when you go on time delay? You will let that fault be there for 20 cycles. Just multiply 16.67 milliseconds times 20. So we are talking about a different type of technology. The inverter cannot conduct that current for more than 10 microseconds. So what you do is you sense the voltage drop across the switch, and when it exceeds 3-4 volts, you interrupt the triggering signals. Right, that's what you normally do. So when you talk about, so why I'm saying this? Because you are going to hear a lot of, as you go and work, that distributed generation increases the fault current. And the answer is, it depends. If distributed generation is a synchronous generator, right, let's say a diesel generator. Let's say that the University of Arkansas gets the diesel generator that they have for emergency, and they are generating power during peak conditions because SWEPCO is paying them $30,000 a year to plus the electricity, so they don't have to. Because what's going to happen if you use distributed generation? Why sometimes distributed generation is used? Well, right. Same thing as you have there. Right? The economic benefit of distributed generation could be release generation capacity. Well, that probably is not so, it's not. But probably release transmission capacity, release distribution system capacity, right? Those are the reasons why distributed generation is used. Because now the power doesn't have to come from your source, right? There is a figure in the textbook, in chapter 1 that we saw at the beginning, right, of this, here it is, right? Figure 11. I have distributed generation, and here they're showing 2 types, or 3 types, right? Here they're showing solar or wind, right? So now, if I'm generating power here to supply this system here, right, I don't need to bring the power from my transmission line, right? And so if this transformer is operating at capacity, right, and by bringing this, I can delay, right, upgrading these transformers. I can delay upgrading that transmission line. In this particular case, the dispersed generation, dispersed storage and generation, or sometimes it's called distributed, right, comes through here, through here, through here. I don't have to upgrade this transformer because it's normally connected on the secondary side of your distribution substation. That's where you connect your solar farm. That's where you connect your wind farm. That's the problem why the little towns in Oklahoma have problem with wind farms. because the voltage, with except of one manufacturer, the voltage is 690 volts, 480 volts. So what is the next step? You know, as I was asking a graduate student the other day, can you have a transformer that goes from 480 to 161 kV? Yeah, there's nothing wrong, right? Just get a book on design of transformers and you're going to design it. But what's the problem? It's not a standard product. And if it's not a standard product, what is going to happen when you pay when you ask a transformer manufacturer, I want a transformer which is 480 volts to 161. It's going to be expensive. So normally what they do is they step up from 480 volt to 13.8 kV or 12.47 or whatever, because there are a lot of manufacturers in that field. And then they're going to have a transformer that will go from 12.47 or 13.8 to whatever is your sub-transmission, 132 kV or 161 kV. So you don't use one step of transformation. You use two at least. So that's what's happened. So what's happened with an induction generator, a wind turbine? What is the problem? Right? Well, at 480, yeah, you cannot send. That's the reason why you increase. But let me see if we can go to the wind part. Well, we can come here. Let's talk about wind. Right? So wind, you have small ones are under 10 kilowatt. Intermediate, they are 10 to 250. Under 10 kilowatt, where are the applications? Your house and below, a farm, you know, rural applications, small loads. If you increase that, you're talking about a community, because you produce sufficient power to supply 10 houses, you know, 20 houses. You got a community. And then you have a wind park, which is more than 250 kilowatt, but you know, here you are talking about 100 megawatt, 200 megawatt. What is the voltage of the generator here? 480 volt. So you are going to step up to 13.8. You are going to use your distribution feeder where your grandpa's house is connected, and then you are going to step up to 161, 345 kV to send that power to Dallas or Oklahoma City. So what's happened with the power produced by the wind? And here it talks about, you know, this is all, there is the reference, but, you know, it tells about that in Latin America and the Caribbean, there was 4 gigawatt of power, in Asia 50, Pacific 2.3, Africa 2.5, North America 42. And, you know, this was taken from here is 2007. We need to update this. Here you look about 2009 wind power capacity, right? Here is where we are. You can see that here, look at that, Texas, right? In this area, they have huge wind farms, right? Also in Oklahoma, also Kansas, Nebraska, all those here, right? So that's basically what you have. Iowa. You see that in this part, there is not much wind because the wind doesn't blow much. California, right? And so here is the capacity, 1,000 megawatt to 9,500, right? And that's basically, this is the equation, basically, that you have for the wind. right? Is the wind velocity to the power of 3. And all the others depend, right, on how you basically design the turbine. And basically that's what you're going to get, right? You're going to get curves of power which are a function of the wind speed. And so what's happening if the wind speed changes? You get different power, right? I need to add probably a figure I don't have here. I need to add a figure that shows probably the power. Right, and here we are using some program that you get in MATLAB Simulink. Right, so for example, this wind turbine, right, at the speed of 14.4 meters per second, right, is giving you this amount of power in per unit. And here is the question is, well, how do you integrate wind turbines? Some of you basically are going to work on this. Well, if you have a permanent magnet synchronous generator, right, basically what you go is you have a variable speed, so you are going to get variable frequency. So what you do is you rectify into a DC link, and from here you use this is a rectifier, and from here you go from a DC to an AC to the grid, and here you have your 60 Hertz transformer to step up the voltage to 13.8 kV, whatever it is. So here you have 480, here you have 13.8 kV. Well, the advantage of this is that you don't need gearboxes. Right? You don't have gearboxes. I don't know about this cheaper. So, and basically, because here you can operate at 150 RPMs, which for a two-pole machine will be a very low frequency, right? But it doesn't matter. Some systems here, what they do is they have a dial bridge followed by a boost converter. So they rectify it into a DC voltage, and then they use a boost converter. So if you are taking Dr. Ann's class, you probably are familiar with that. The other type of machine is the okay, let me go here. And this allows you to harvest the most power from the wind. The system is complex, right? Because now you need to, the power electronics has to be sized to what? To process 100% of the power. So it's expensive, right? You have to buy semiconductor devices that are able to push current, right, 100% of the rated current, right? But the speed of the wind can change. You got the greatest range, so you can harvest the most power. But it's the most expensive system. The next one that allows you to capture power, right? The permanent magnet is the one that gives you the highest power. The next one, going down, is the doubly fed induction generator. And basically what you do is, you have here a transformer, which has 3 windings, right? One to go as before, and this one a third winding, where basically the rotor. So now you have to, instead of having a squirrel cage on the rotor of the induction motor or induction generator, you have a one rotor. You go to a more expensive machine. But controlling the electronics, you can change the resistance of the rotor. And I don't know if in energy system you look at in detail to a one-rod induction motor, but that's basically what's happening. And so that allows you to increase the operating range of the wind turbine compared to the induction generator. So that's what you have. The problem with the wind farm, right? Here, for example, you have a utility system, 161. You need a power transformer that you have seen it. And here, this is going to be 480, right, 680, so you need a transformer. You connect them in parallel. Sometimes, instead of having just a single transformer, each wind turbine will have a dedicated transformer. And the problems that you have is voltage fluctuation, flicker. Because as the power changes, what's happening? The current changes. As the current changes, what's happening? The voltage drop changes. So you understand what voltage fluctuations are after having done the voltage regulation. That's if the frequency, what is flicker? Flicker normally is concentrated for frequencies under 8 to 10 hertz. So if that variation of the voltage fluctuation is sort of periodic and at a frequency under 10 hertz, you are going to notice. If this is at 1 kilohertz, your eyes are not going to adapt, right, to see. So it has to be very low, slow-moving changes of the voltage. Now, if these are induction generators, not the doubly fed, just the typical, what do they need to operate? They need reactive power. And so where is the reactive power coming? It's coming from here. So the reactive power has to travel here. That's the reason why this wind farm, normally they have some shunt capacitors here, the switch type, to provide that lagging reactive power that the leading reactive power that the induction generator requires. So if you look at some of the topologies, this is a control rectifier, a DC link, and this is the inverter, and here is 480. Now there is one company, I believe it's a company in Spain, that is trying to get a wind turbine that can connect at 6,600 volts, line to line. And they're trying to go for 10 megawatt. Right. Now, at the present time, the most common is 3 megawatt, 5 megawatt. In the United States, the number one is General Electric. And this company is trying to go into 10 megawatt, particularly because what does it mean? Well, if you are thinking of offshore applications, right, you are going to, right, you know, if you have 3 megawatt and you have 300 megawatt farm, how many wind turbines, right? You need 100, right? So it means 100 structures that you have to put in the ocean. Now, if you have 10 megawatt, how many turbines? Right? So you just do the number, right? With 30 turbines, right? That means 30 structures that I have to set up, right? So that's the reason why they're trying to increase. What does it happen? What do you need, right? If you look at the equation, right? If the wind is the same, right? What has to change? The rest has to change the swept area, right? So it has to change the diameter of the blade. And what's happened with the diameter of the blade? Well, instead of being 50 meters has to go to 100 or whatever, right? So now you start having some big structures, right? And you see how some of these things that are happening, you can look at an equation like this and say, well, if I have the same wind, but now the power of I want to extract more power, I have to change this. Well, I cannot change the air, right? The air density stays the same. The only thing that I can change is basically the swept area, right? Which is the one covered by, like that. In this particular case, right, it allows you to take power from here over there, and then you can send it back. Normally you don't have that requirement. So you could basically go to a unidirectional power converter, because power goes from the wind turbine to the grid. It doesn't go from the grid to the wind turbine, right? If the power goes from the utility to the wind turbine, what do you have? A big fan, right? So now it wouldn't be an induction generator, it would be an induction motor, right? And so the wind turbine would be working with a fan, right? And I don't think that you need a fan in that application, right? It would be unique, but you wouldn't have many takers. And now, if you want to increase the voltage that you get here, right, this is basically here, right, this is a 2-level because you have a positive and a negative. If you want to increase the voltage, you go to a 3-level, right, and that's a 3-level converter. And what's the problem here? The problem is that there are not many manufacturers of that. And what's happening if the only manufacturer of that goes bankrupt? You are stuck with a lot of wind turbines that have that product, and you don't have you don't have parts, you don't know how to repair, things like that. So the manufacturer of wind turbines, by the way, the manufacturer of wind turbines, normally they are good. GE is a good integrator because they can do they can do the towers, they can do the blades, they can do everything. But Vestas, for example, right, which is the largest wind, they buy the electric machine from somebody else, right? Probably they go to China to buy that. They buy the power electronics from somebody else. And they probably, their specialty must be to all the steel, right, in producing the blades. The blade, you know, we used to have a company in Little Rock producing blades, right? So that's basically the problem with this technology. It works because you can get to a higher voltage, but the problem is you got a problem. Well, let's talk about, we were talking about wind the other day. Let's see. This is basically, it's called a 2-level because you have a positive bus, a negative bus. You got an electrolytic capacitor. This is a control, you got control switches, IGBTs. Here you got control switches. This is a control rectifier. And so this is called back-to-back. It's called 2-level because you have a positive and a negative. And here basically you have the utility, but in real life, right, what you got a power transformer. Most of the time this is connected here, right? You have individual. It's a matter of cost. This is a 3-level. We talked, well, this is still a 2-level because you have a positive and a negative. If you do like that, what you're going to have in the capacitor is 6 times the fundamental component, so 360 hertz. That's 4. And here you have an inverter. And the inverter can be controlled to provide either P, real power, or Q. This is what is called a multi-level power converter. It's a diode clamp because you have diodes here. There is others that are called flying capacitors. So instead of having those diodes, you have capacitors. But basically you have three levels because you got positive, you got negative, and you got the midpoint, right? And so basically the advantage of this is that you can use lower voltage devices which are more efficient, right? You know, why they are more efficient? Well, let's think about that you have to climb a 10-yard or 20-feet tower, and another person has to climb a 5-feet tower, right? Well, if the voltage, think of the height as being the voltage, right? So the device is, even if it's the same technology, is going to take less time to reach 5 feet, right, or 5 volts than 20 volts, right? So that's the reason why using lower voltage devices, right, are more efficient. They have less losses, energy losses, than a high voltage device. A typical case is, for example, you have 6,500 volts IGBTs. If you look at the switching losses, right, they are very lossy devices. Means that how do you remove the losses out of a semiconductor device? You have to have what is called a thermal management system, which is basically a heat sink, an aluminum heat sink. So if you have a device that has lower switching losses, and that's the reason why there is a lot of interest in what is called silicon carbide, right, devices, which are targeted for high voltage applications. The problem with the silicon carbide devices is that they don't have the current rating that you need for power, for utility applications. It will be probably 5 years from now until you got a device that is 800 amps. With silicon, technology is more mature, but we have been working on silicon since the 1960s, right, where silicon carbide. Now there are a lot of lessons that has been learned from the silicon development, so we are hoping that the silicon carbide will move faster. But this is a 3-level, and like I said, some manufacturers are. The problem with this is that a lot of these, we finished on Tuesday saying a lot of these manufacturers are in reality integrators. They buy the parts from other companies and they put it together. And so if they don't have sufficient vendors, more than one, right? If you want to buy a computer, right? Why the PC, the desktop is so cheap? Because it's a commodity. You got HP, you got a Compaq, you got Dell, you got, Acer, you got Asus, you got so many of them that they are all competing. So the price is cheap. Do you think that if the only manufacturer of desktop would be IBM, right, you would be paying what you're paying for a desktop? No. You will be saving like buying that fancy car, right? So you could buy a desktop, right? So the reason is that basically there are many vendors is what bring the price down. This is the problem here, is that you don't have that many vendors. Well, wind is a variable resource. This is the problem. Unlike now, if you look at the trees outside, wind is not blowing, right? So what about if you are depending on wind? It's variable. By the minute, I would say that it's even by the second, right? By the hour, by the month, by the year. Right? The spring, fall, spring seems to be windy in northwest Arkansas. In July and August it's very hot. There is nothing moves normally. So if you are going to invest on a wind farm, are you going to invest $3,000 per kilowatt or 2,000, whatever its prices are coming down, to generate only from October to March? No. While in Oklahoma, Kansas, is windy 12 months of the year. So that's what it means here by year. You know, the load demand. The load is, I need to power this building, whether there is wind or not. In fact, most of the wind, in some cases, it blows at 3 a.m., 4 a.m., when everyone is sleeping. Most people are sleeping, right? So when you have wind blowing, the demand is not there. What doesn't mean is that if you look at if you remember that figure A15, A16 in chapter 8 that talks about reactive power, but there is a similar figure, or several figures in chapter 2 that shows the graph, right? So the peak for power occurs between 5 and 9 p.m. Well, peak wind generation normally is outside those hours, right? So when the load is high, the wind is not available. Also, it's not dispatchable. What means dispatchable? Well, you are part of a market. If you are selling power, and you are going to say, I'm going to sell you 100 megawatt from 10 a.m. to 2 p.m. and you put that into the market, there is a 1 day ahead, there is a 1 hour ahead, and there are 15 minutes ahead. The cheapest one is 1 day ahead. Well, there are also contracts, right? The city of North Little Rock contract with some providers that are going to get, let's say, 300 megawatt every day. You know, they might have, obviously they have a low curve, whether it's summer, whether they are summer peaking or winter peaking, you know. But they contract that are going to get X amount of power at a certain rate. But then what do they do with the difference? They call the unbalanced market. The balance is if I contract to buy 300 megawatt and I'm using 300 megawatt, it's a balanced market. Now what about if I'm using 200? The guy that sold me 300 still wants the money for 300. So you have to be able to go and say, okay, let me go and sell those 100 megawatt. Normally if you are using less than what you forecasted, probably because everyone is using less, right? So it will be hard to sell that power. Now you are selling 200, you are buying 300, power cannot be stored, right? So that's why it's important for an electric utility to have all these programs that basically can help you to forecast what is your load curve and where are your demand. Because if you know, every day you are off by 100 megawatt, it means that you need less. Sooner or later you are going to go under, you are going to go bankrupt, right? But the other thing is power is not dispatchable. I cannot tell someone I'm going to provide 200 megawatt for the next hour. Because if the wind stops, what do I do? That's the reason why people talk about energy storage. Well, the problem with energy storage is it's very expensive. So it's not a very good proposition. And today we were talking wind power on an economic dispatch program is considered as a negative load. Remember, input power is equal to what? Output power plus the losses. Reactive power, Q source, equal to Q load plus whatever you have in the lines. Wind is considered as a negative load. It's on the right-hand side of the equation, but with a minus sign. Why? Because the economics dispatch software doesn't know. If you have taken power system analysis with Dr. McCann, you are aware of it, probably because he deals with economic dispatch. All those code, everything, doesn't know how to deal with the wind. Another thing is that legislation in the form of a renewable portfolio standard, RPS, they require that you have to buy wind. You have to buy renewable energy power. If you look at California, what is their goal for, I think, 220, 33% for 220, right, or 230? 220, right? 33%. So they are going to have some generation that is going to be changing, which is 33% of the country. Now, if you look at California, and that's probably applicable to your topic, they have come up with some legislation encouraging energy storage. Because when the wind drops, the energy storage is going to provide the difference. When the wind produces more power than you need, then the energy storage is going to absorb. Some of my students have done studies. How do what about if I have my energy storage 100% charged and the wind keeps producing more? You got a problem, right? Because you cannot absorb any power. So there are some software, there are some, you have some forecasting. Some of you that like about control systems, it's called Kalman filter, where you have to predict what is going to happen. Now, it's more difficult to predict what's going to happen with the wind tomorrow, but you can predict what's going to happen with the wind in 2-3 hours. But in order to predict, what do you need? You need to have measurements, right? And that means wind velocity, all, So it's very complicated. So there are a lot of researchers that are, and some of them, they are able to sell their ideas to be implemented in a software that is just basically forecasting what is wind generation. Because someone at the control center has to make decisions whether, if they are forecasting that the wind is going to increase and the power stays constant, the load power stays constant, they have to tell some other generator, normally it's a natural gas in this country, could be coal-fired power plant, but they don't have much margin, to start dropping power. They have to start sending a control signal that at 1 p.m. they need to start dropping power because the wind, right? And obviously that is, so the balancing, that's the balancing of the market, right? You have to balance the generation to the load. So are storage systems necessary for wind? And the answer is yes. Because if you have energy storage, which is economical, you turn wind into dispatchable. And then wind will have much more value. What can you use as a storage? Batteries. What's the problem with battery? There is not a good battery. They haven't developed a good battery. Lithium ion, for example, is one that are talking, they're using polymers to improve the electrode, things like that, but still the densities is about 600 watts per liter. Right, so it's not very good. Superconducting magnetic energy, superconducting magnetic storage, once again, a lot of these you have to talk about technologies that you can scale up. Right, it's very nice if you do something, oh wow, look at this battery, right? Perfect. I got 10,000 watts per liter, right? Right? Well, can you now scale up to 10 megawatt? Nope. This is how far we can do it, right? So that's something that you have to look with the technology. So when you read an article, you need to think about, is this scalable? Can I go from, obviously, a lot of people would like to have 10,000 watts, right? Remember that I talked for the lithium ion is 600 watts per liter. So if you have a liter, right, you know, which probably will be this volume, right, is 600 watts. So if you are going to have 10 megawatt, how many of these books you have, right? So you need to have a lot of books, right? So that's the problem with the technology. The base case for energy storage, what is this? It's Beaver Dam, right? You can store water there as long as you want, right? And that is called the base case. Some folks, they talk about compressed, well, probably we are going to get there, right? And that's what it is, pump hydroelectric storage, right? That's what it is. You have two reservoirs, one at the bottom, one at the top. So when you need to generate, you let water from the top reservoir going down to the bottom, right? And then at night, 3 a.m., when that coal-fired power plant is running, right, and you don't want to bring down the generation because of the mechanical issues or the thermal fatigue that you can have, you use that cheap energy to pump water from the lower reservoir to the top one. What's the problem? Well, you have to have some sort of a level difference, right? Otherwise, if you are going to create that artificially, right, you need to have a lot of concrete, right? So in the mountains, right, where you could have, you know, a natural reservoir, right? You could, I don't know, but you know, Beaver Dam, for example, right? That is an area where it's not very populated, and you could have two reservoirs, and you pump. They have to be close, right? And then compressed air storage. This is something that is being, sometimes they talk about when it comes to Texas, right? Because in Texas they have a lot of oil fields, right? And they have taken all the oil out of that. And so what is left? The reservoir, right? And so then you can pump air there under pressure, right? So you use the cheap energy, right, or the excess energy of the wind to drive a compressor that will pump air into a container, a cave. And then, when you need the power at 5 p.m., right, remember the wind is blowing at 3 a.m., so I can use that power to charge, to put compressed air into the cave, and then at 5 p.m. or 4 p.m. when I need that power, the compressor runs as a generator. What's the problem? Well, you need to have the cave. Because otherwise, if you are going to build the container, it's expensive. And what's happened with the cave? And normally the cave, they're not perfect sealed, right? They have some openings and they get there. And so the pressure to be able to drive the turbine that will drive the generator doesn't stay at the right value for a long time. It's not that you can cap the cave and come back in a week and use it, right? So normally if you do it 3 a.m. in the morning, right, you fill in the cave with compressed air. Also doesn't have to be a big one, right, because otherwise what's happening? You need a lot of air, right, to build pressure. And so, and then you use it at 5 p.m., 4 p.m. So you have basically a 12-hour cycle. Storage. And storage is going to become more important because what's happening is as there is more research, maybe they found new materials. I think that Manuel is looking at one that has just show up at, some people are talking about using molten salt, right? The University of Arkansas, the Department of Civil Engineering, Dr. Selvan, probably you have seen something where they're using, if you've been to Engineering South, they use solar panel, right, to capture that energy, and then they drive a current into concrete, right, and so they heat up the concrete. And so they use the concrete, a special type of concrete, because of the thermal mass. Well, the problem is that you have to use it quickly, right? Because if tonight it's going to be 20 degrees, right, Monday I think it's going to be 19 degrees. Well, let me tell you, that heat is going to go to heat up the area, right? So there are advantages and disadvantages with any technology. And efficiency is basically, and so this is the pump storage, right? We talk about the top reservoir, the bottom one, and basically, you come here, and basically that's what you got, and so basically what you need is an electric machine that can operate in reverse, right? The pump also operates in reverse. In one direction of rotation is a pump, in the other is a turbine, right? And the largest one, I don't know if I have a picture here, but there are basically, this is the pump storage, right? Here is another one. So let's look at what is this busy picture. And I don't see a reference, so it looks like the student. But now, here what you have is hours, minutes, and seconds. And here you have 1 kilowatt, and here you have 1 million kilowatt, right? Which is equal to a gigawatt, right? So you go from very large to very small. Now, energy storage will have many applications. Can be energy management. Could be for power quality and uninterrupted power supplies. And then could be bridging. Right. For power quality and uninterrupted power supplies, you go from second to minutes. Right. You have a sag. The voltage drops. Right. Or you have a fault for 2-3 minutes. You have to keep that server farm, right? All the server farms, the database, right? The computers at this university, they are all having a diesel generator, right? But you could use energy storage. Well, when you look at here you have the technologies and the applications. Right, this is the pump storage hydro, very large. This is a reservoir. This is Beaver Dam, right? I'm not saying that you could use. You need to have a lower reservoir that you don't have in the case of Beaver Dam or Lake Fort Smith. This is the compressed air energy storage, right? You can see it's not as big as the hydroelectric, but it's big, and it can give you for several hours. Here is SMES, superconducting magnetic energy storage. Well, you can get a lot of power, but just seconds. So the application of these two technologies are different. SMES is used for very short momentary interruptions, where you need to have power provided by seconds. So here, power is important. What is energy? It's the integral of power over time, right? So here, what you are getting? A lot of power, a lot of time, a lot of energy. Here you get a lot of power, but for a very short period of time. So the amount of energy involved there is very small. high-power supercapacitors. This is something that, once again, you know, we hear about using energy storage and we use about supercapacitors. Once again, the supercapacitors are for very short period of time. Honda had a electric vehicle with a fuel cell, and it has short-circuit supercapacitors. Why were there? Because the fuel cell cannot provide power changes instantaneously. It takes a while, because of the way that the fuel cell works, to go from 10 kilowatt to 15 kilowatt. So what's happened when you are going on 71 and you are trying to pass this truck, and so you go there, and then suddenly you see that a car is coming in front of you, and you need to accelerate, because otherwise you're going to have an accident. You need a lot of power at that time to accelerate the car. Well, the fuel cell has a very slow response. Well, what is a capacitor? The capacitors don't like the change of voltage, right? And they are used as a filters where you don't want the voltage to change. Normally they are the output of your converters, because you want to have a stabilized DC bus. Well, the supercapacitor is the one that is going to give you that acceleration current that the electric motor of the vehicle needs, so you can accelerate and you can pass the track and you don't get into an accident. But it's going to give it for a certain period of time. You cannot keep going forever. If you have 10 tracks, one after the other, and there is no room to go there, I wouldn't go, because probably at some point the supercapacitor is going to be flat. Right. Here, high-power flywheels. This is the same. What is the energy of a capacitor? The energy of the capacitor is 1/2 of C, right? The capacitance times the voltage to the square. Why they call supercapacitors? Because C is in farads, right? Remember, the normal technology that you have, they are millifarad, microfarads, picofarad, right? The only one that is in farad is the supercapacitor, right? That's the reason why they call it super. Well, but there is a limit that you can go, right? You cannot make C equal infinite, because then you wouldn't have a space for anything else, right? So, V. So what does it happen for the supercapacitor to provide energy? V has to drop. If V stays constant, what is the energy stored on the capacitor? Stays constant. So you're not getting any energy from the capacitor. So what is the energy if now the voltage drops to 1/2? It's V divided by 2 to the square. What is that? V to the square divided by 4, right? So that's the reason why the regimes that you normally use for the ultracapacitors or supercapacitors is from rated voltage to 1/2 of the rated voltage. And so what you need some power electronics, a DC to DC converter that makes the step up, right, that interfaces with a constant DC bus. Flywheels, which are here, and they can give you a little bit more. What is the energy of a flywheel? Proportional to what? Yeah, the inertia, but the velocity to what? To the power of 2, right? It's velocity to the square. So what are you going to do? Drop the speed to 1/2. Because once that the speed dropped to 1/2, what's happening? You have taken 75% of the energy. And it's not worthwhile to take the other 25% to complete it, bring it to a slow down. Why? Because then you have to bring it up to a rated speed, right, to complete the cycle. You discharge, you charge it. You start, same with the ultracapacitor. You charge it, you discharge it. You charge it, you discharge it. So normally these flywheels or capacitors, they operate between rated speed or rated voltage and half of the speed. Wow. Now if you look at here, here is where the batteries are, right? LAB, lead acid batteries, right? Where are the LAB? Here, right? I read an article the other day that Europe is bringing some regulations that probably are going to phase out of the market the LAB, right, because of the lead. Sodium sulfur batteries, SSB, here. Well, the sodium sulfur battery, they've been taken out, the sodium is heated up to 300 degrees centigrade, and they have had some fires, so they have been taken out of the market for a while, right? Float batteries, these are good, they should be here, right? They give you a lot of that and power. The problem with the float batteries, basically efficiencies are about 80%. When it comes to battery, you have to take into account the return trip efficiency. What is the return trip efficiency? You have to charge the battery. Think of the battery, the model of a battery, the simplest one, is like your infinite bus, right? You have the ideal voltage source, and you have the short circuit impedance, right? That was the internal impedance of your infinite bus, to account for the fact that you don't have an ideal voltage source, that there is a voltage drop as the current increases. Well, a battery, the simplest model is a DC source with a resistor. And so what's happened? When I'm charging that DC source, I'm going to lose power on that resistor. When I'm discharging that, I'm losing power on that resistor. So that's the reason why we talk about the return efficiency. And so the flow, the best one in terms of the return efficiency is the lithium ion. You are about 95%. The float battery is about 80%, 85%. So that's the reason. But the advantage of the float battery is that power and energy are not related. You can increase the energy capability of the float battery and still have the same power capability. Basically, the float batteries, there are two containers, and basically an electrolyte is being circulated. And if you want more energy, what you do is you put more containers, right? Here, lithium-ion batteries. They are where they are, here, right? See, there are NiCad batteries. What's the problem with NiCad batteries? Nickel cadmium. What's the problem? See, when you look at this, some of these batteries, you have to look at issues like, what's the problem with cadmium? It's toxic, right? You cannot recycle. You cannot put it on the garbage can and send it to the landfill. You shouldn't, right? So that's the problem, right? Why some of these technologies will never make it. Because you have to look at what is the concern with the environment. Here it says other advanced batteries, and you're going to, and probably, you know, they're using zinc air batteries. You know, they're using for scooters, you know. So there are different type of designs that pump hydroelectric storage in a smart grid. Basically what you do is that here said pump hydroelectric storage shift effectively load and generation. What we were talking about here, remember, is that most of the time when you have wind, right, what's happened? It's at 3 a.m. Everyone is sleeping. So what do? I need the wind to blow at 5 p.m. Right? So how do you do that shifting? And that's basically where pump hydroelectric storage is, to use cheap energy at 3 a.m. from the wind to store, right? In reality, you cannot store power. You have to consume it but you can store it in a battery. Now the problem, if you are talking about 10 kilowatt, it's okay. The batteries are not big. But if you are talking about 100 megawatt, like in the case of a wind farm, now you need a lot of batteries. So pump storage is a better alternative. The problem, you need some reservoir, right? And here is where basically this is this diagram, right? This is the load curve that you have, right? You go there, you got, and here you have base load generation, right? That you don't want to change it. Here, really, you need only this. What you do is the difference, where you use this power that the base load generation is given to charge the reservoir. So basically what you have is the base load, which is called fire power plants, right? You keep them operating constant. It doesn't matter, right, what is the time of the day. So whenever you need power into the grid, your base load goes into the grid. But whenever the grid needs less power, goes into the storage. It's very simple, the concept. That's what we talk about with compressed air, right? You have an electric motor that basically draws power from the grid, and then basically you have a compressor. Here shows two different systems. You go through some air cooling, and then it goes to an underground salt cavern, right? In Texas, New Mexico, you have a lot of them. Then when you need to get the power out, you go through here, you go through a turbine, through a generator, and then you pump the power back into the grid, right? Obviously here you're going to have some losses. You're going to have some losses here, you have some losses here, and then you're going to go into this turbine, and here you're going to have some losses here into the process, and then the generator has some losses and you inject. So that is the retain efficiency, right? You have to account from the efficiency of this whole cycle, right? You come back to the same point, right? So that's, what are we going to call that efficiency? Retain, because we retain to the same point, right? And so this is the key for, but mainly, like I say, you have to have a carbon, you have to have a natural reservoir. If you are going to build your reservoir, is superconducting storage. Basically, it's here is a regular coil, but it's a high inductance coil. Basically, the problem here is it's a superconducting material. Now, there is nothing that works at ambient temperature, so you have to have some cryogenic equipment to keep it superconducting, right? So you got a problem there. What superconducting magnetic energy storage, the way that it works is like this. This is your AC source, this is your transformer, and here what you have is a DC to AC. So you go from DC to AC, you are inverting, right? So you have an inverter, and here what you have is your superconducting coil, right? And so what you do is you close the switch, so current circulates here, right? This is, in this way. That's how it's recirculating, right? If this is superconducting, what is the resistance? 0, right? So that means that the energy doesn't get wasted, right? If I use an inductor at ambient temperature, the resistance is going to basically dissipate all the energy that I have here. Since the resistance is 0, right, in an inductor I have 0 losses, so the energy stays constant. That's the cryogenic system that I need to have this in the superconducting state. When I need to inject power, I open the switch. So what's happened with the coil? There are two functions, right? If you are an expert on power electronics, right, there are two things that you learn. Inductors oppose the change of current, capacitors oppose the change of voltages. So anytime that you need to have a constant voltage, you are going to put an output capacitor. If you go back to all your experiments or your senior design 1, if you have built some electronic circuit with an op-amp or something like that, what do you have at the output? A capacitor, a filter capacitor, because that's the function, is to have a 5-volt power supply, a 15-volt power supply. You will use an inductor when you want to have a DC current, right? Sorry, no change in the current. And so what's happened is, because of the coil, the current here on the coil cannot change, and so the current now is going to go basically through the inverter into the grid. But remember, the amount of energy here I don't know what's happening with the computer. Probably because I opened from the man. Where is the superconducting? Here, SMS, right? So this SMS is here, right? So I can get a lot of power, right? But very short period of time, right? So that's the importance of that. And here are some of the applications, right? And you see it's always seconds. When you go to hours, I have my problem with here hours. You know, I don't think that, well, let me put it. Yeah, I can have 10 megawatt, 100 megawatt of batteries, right? That's no problem. They are technically, just get your paper and your pencil and you can figure out 100 megawatt of batteries. That's not a problem. It's crazy, but right? That doesn't mean that the fact that you can design it, right, that makes sense, right? A scientist might do something like that, but as an engineer, we have to look at the cost, right? So it doesn't make sense from the cost point of view, right? So once again, here they said hours. Well, you need a huge coil there. Or maybe you are envisioning having 10 of them in parallel, right, so you can get for hours, right? So that's what I'm saying is, I think it's mainly around seconds, you know, I'm not sure. This was drawn by a student, but probably looking at something else. So for integration to smart grids, renewable energy sources of energy may require advanced energy storage systems with the following benefits: improving system reliability, enhancing dynamic stability, improving power quality, enhancing transmission capacity, increasing dispatchability of renewable energy sources, right? So energy storage has been identified as an important component. Now the problem is that in this country the energy storage is not being viewed as a system resource where you could transfer the cost of the energy storage to all the customers, not just to those taking advantage of that. If it were a system resource, then you could transfer the $10 million that costs, right, an energy storage system over a larger pool of customers. That means that the increase in the electric rate will not be that much. But at the present time, the utility is not taking that view. They are using research and development dollars, with the government paying 50%. But if they now they are allowing, for example, energy storage to start playing into the real-time market. Sometimes, for example, spinning reserve. Spinning reserve is when you have a generator that is rotating. That's why they call it spinning, but it's in reserve. It's not generating, or it's generating very little, 25%. Like a natural gas generator, that's the peaking plant in Tontitown, the peaking plant in Elkins. And so when there is a demand for more power, the generator that is rotating starts generating more. So you want me to have a generator rotating, I have to pay for Joe Block Jr., right? I have to buy the generator, right? You have an infrastructure. So when you participate in a spinning reserve, you get paid. Whether you are being asked upon to generate power or not, you are getting paid certain amount, right, by doing nothing, right? It's like, just sit there and someone comes and needs you, but you get paid, right? So this is the same. The spinning reserve is a generator that is rotating, is spinning, is in reserve to take into account to balance the system. P generation, the generation has to be equal to the load. Well, what about energy storage? Right, a battery can be used as a spinning reserve. In the Northeast, New York, New Hampshire, all those places, they're starting to accept that energy storage can be a participant. And we have run some simulations using historical data, and most of the time the spinning reserve is not being called to participate. Why? Because remember, what did I tell you? If someone that needs 300 megawatt and then happens to be needing only 200, right, very soon that utility is going to be out of business. So the electric utilities, they have a lot of software that they can basically predict what the generation would be. So most of the time you don't need to use them, but you have to have in case. right? And so, basically, and you get paid for a spinning reserve. Sometimes you can use energy storage for frequency regulation. What's happening if the power increases? The low power. And the generator cannot provide that. The generator speed starts going down. And they are changing. Frequency has to be kept between 59.7 hertz and 60.2, something like that. Very strict control. So that means that whenever there is a big increase in the demand of power, you need power immediately. Energy storage can do that. Why? Because you have power electronics. Instantaneously you can tell those IGBT start switching and start providing power. If you tell that natural gas generator is going to take 2, 4, 5 seconds or more, so you're going to have a drop, right? So that's the reason why it's attractive. The problem that, a natural gas generator is a known commodity, right? We know what it is. We know, it has been. There are several manufacturers. It's a very competitive, cost-effective solution, particularly in this country where you have a lot of natural gas. There you have some of the references, and I think let's go do something that. So I dealt with wind. I don't know why I started first with wind, but let's start talking a little bit about solar on the last minutes. Solar is having a problem lately. And there are different technologies here. What you see there on the top, and they're putting a lot of emphasis on that lately. Basically, you don't have a solar cell, like we know. Basically, what you have all those plates that reflect here, right? All the suns are aimed to this tower to heat up an oil or water, and that is being used to drive a regular turbine. Steam, right? And then you drive. That's how you produce steam. Instead of burning coal, that's how you do it. Here, where the cursor is, there is a pipe with oil. And so the sun heats that plate, that convex plate, and then it's designed that aims to that pipe, and then you heat that. Now, in order to have the oil, what do you need? A pipe. For the oil to be heated, what do you need? The heat to go through the pipe. So you have some losses there, right? But that oil then is being taken to a central facility where it's used to heat up something. And that's a prototype. Both of them are in California. And this is the solar panel that basically we have two of them on the top of senior design, right, for some research. Lately, right, so you can use solar energy for lighting, right, or to generate electricity, but lately there is a lot of attention because of the cost on producing heat and hot water. If you go to the Mediterranean, any of the Greek islands, you will see, all these hot water systems on the top of the houses. Because there it doesn't rain, right? If you look at southern Italy, southern Spain, northern Africa, right? It's mainly, right, very desert type of, very arid, right? And so, makes sense. A lot of time that you have sun and they use that for heating water. This is what you have. This is photovoltaic solar resource. You can see why, a lot of things happen in New Mexico, Arizona, Southern California, right? You will see that in this area doesn't make. This has to do the amount of watts per meter square. And, this is 6.86 kilowatt hour per square meter per day. You see, Arkansas is not that bad, right? But, here really the payback period will be too long. This is the concentrating solar resource, right? This is the concentrating solar, right? Incidentally, this company, Solar One, I think has gone under now. But a lot of changes in this industry. But here is basically, you could see, this is the area where, so if you are going to produce a product, right, you got an area, right? This is the typical model for a solar cell. It's a current source, a diode, and you have a resistor, and you have arrays. So what's going to happen when the voltage produced by this current source is about 0.7, 1 volt? That diode is forward biased, right? So that's basically, it's a little bit about the limitation, right? And so what you do is you have many of these solar cells that you stack them up in series, right? So when you are talking about a 36-volt solar panel, you can figure out how many of those solar cells are stacked up in series. And how do you get the current? You put solar cells in parallel, right? So basically this is the symbol for a solar panel, right? Or a solar cell, right? And that's photovoltaic, that's what PV stands for. And basically that's the model that you have. So when you integrate this into a distribution system, what you have a PV system. This is about 20 volts to 25 volts. And here what you have. If you are at home, you got 120. So how do you go from 20 volt, 25 volt DC to 120 volt RMS? Well, this could be the utility system, the power grid. But basically you need to have some power electronics every time that you go from DC to AC or AC to DC. But also you have to have some boosting action. Right, you have to boost the voltage from 25 volts to, if you are injecting into 120 volts RMS here, you need to have probably a DC bus of 200 volts, at least, right? Because the conversion process from DC to AC doesn't come free. You're going to generate harmonics, and you have to filter them. And so that the voltage drop on your harmonic filters need to be taken into account. Obviously, you need some monitoring and control. So if you get involved in power electronics, you need to know about power, you need to know electronic, you need to know about control, lots of things. These are the photovoltaic systems configuration. The central converter is probably, so far, is the winner. Remember that in the past, our department has participated on setting up a system on the top of the Fayetteville Public Library. There is another system on the top of the Enterprise Building on Engineering South, or the Arkansas Research and Technology part. And the same similar design has been done in the city of North Little Rock, and also the L'Oreal plant in North Little Rock. And basically that's what I said. To get to the voltage, what you do is you stack them up, the panels, in series. You need a diode so current doesn't flow right in the opposite direction, so you don't do this one doesn't fit here, right? Because if what's happened with this panel gets shaded, right? The voltage here is going to be lower, so you don't want basically these three panels that are not shaded to inject current here, right? So that's the reason why you need a diode there. And basically here you get the voltage by connecting in series, you get the current by connecting this in parallel. This is called a string. Each of these is called a string, right? And here is what you call a string converter. Instead of having, this is the same case with a central converter, but instead of having two strings, basically you have two inverters, right? If you do that, they operate separately, right? You got more flexibility. What's the problem? I just went from one inverter to two. They are not the same rated power. Well, those two, the power of each of these is half of this, right? But, you know, it's not that it costs, two of them cost the same as one of the other, right? It's not, doesn't work like that. Here, what you got, this equal sign here means DC. This is AC. So here you go from DC to AC. There is what is called a two-stage. You have a DC to DC, right? DC, DC. So you have a string and a string from DC to DC. And then you go to a common DC bus where you go from DC to AC. There are some folks that are. The problem here is that when you have a cloud, and this is a big problem, when you have a cloud, let's say covered in this panel, you lost the entire string. So now your power generation went down by half, right? So people are trying to say, well, how can I generate more power? Well, the purpose of this DC to DC converter is that somehow you can overcome the lower voltage that you're getting here, and you use the boost function. Here, this is what Luciano is working for his doctoral work. It's called a macroinverter, where you have a single panel and a single converter. The problem is that now suddenly you are adding the cost. And what you hope to is that because you are going to generate more power, the extra power helps you to pay for the additional cost. And so that's the reason why we have two panels on the top of senior design to do work on that. This is another, and this is a topology. Right here you have the panels connected in series, and that's the string diode. And here you have, in this case, you have a capacitor, right? Why do you have a capacitor? Right? Remember, when the panel cannot provide you the load, right, because whatever, because the sun is not shining very hard, what are you having? The energy comes. Also the panel, right, when, remember, the capacitor can give you any current. Well, not any, but can change the current quickly. And so any changes, any transient on the AC side can be provided by this capacitor. So the capacitor there is for improved dynamic response. This is the inverter, and here you have a single phase transformer if you want to up. And this inductor and this capacitor here, right, this is a DC capacitor, this is an AC capacitor, and this is the output filter. because here the output is a PWM signal, the utility is sinusoidal, they are not equal, right? So someone has to take the difference. Now, when you have a single-phase transformer, you also have the leakage inductance of the transformer. So you have to take into account that single-phase transformer as part of your filtering requirement. This would be three-phase, same story. So this is the output filter, this is the inverter, and here is like that. So it's very hard to compete with this in terms of cost. Even if when there is a cloud covering this panel and you only produce half, right? This is just the macroinverter topology, right? So here you have a panel, you have a diode there, right? And here you have what is called a full bridge, an H bridge, right? Then you have a high frequency transformer. Here you have a diode bridge rectifier, and here the output, you have an inductor, because the output is a thyristor bridge, so this is acting as a current source, right? And you are injecting a current into the utility. Once again, power electronics. Now, the problem with this topology is that you have 4 switches on the low voltage. Each switch costs money. You need, right? The Department of Energy is trying to have this to, what is 10 cents or 18 cents per watt? 18. Yeah, 18 cents per watt. So if you think that that power is about 200 watt, right? So it's about what, $40, under $40 per inverter. And at the present time, they are about 50 cents to 60 cents per watt. So there is a lot of work to be done to bring the cost to 18 cents per watt. High-frequency transformer requires to use better high-frequency materials, magnetic materials. Okay, and here what you have, the rest are more topologies. These are the different type of solar cells, and those are the reference.